Between the classification and the regression trees, classification trees are the more popular use of decision trees technique. So we will discuss classification trees first. In addition, many of the concepts related to classification trees, such as split search and pruning, are relevant and applied to regression trees as well. So understanding how classification trees are constructed would help you understand regression trees that we will discuss later. For supervised data mining problems, where the target variables are categorical or class memberships, we would construct classification trees. When building a classification tree, we split the cases in the training dataset into increasingly pure subsets to build the tree. At the leaf nodes, we use the majority rule to classify cases to the predominant class the cases in that node belong to. For example, if 80% of the cases in the leaf node belong to the target class or success class, then we would classify any new cases that land in the leaf node into the target or success class. And the predicted probability of the case belonging to the target class is 80%, and the probability of the case belonging to the non-target class would be 1 minus 80% or 20% for a binary class problem. This leads to two questions. 1. How do we define pure subsets? And 2. How do we split the cases to achieve pure subsets? Well, the answers to these two questions all lie in a computerized algorithm called the split search algorithm. Split search is at the heart of decision trees technique. It is also referred to as recursive partitioning, as it repeatedly split the cases into two parts in order to achieve maximum homogeneity or purity within each part. The division is accomplished recursively because each new division is dependent on the previous divisions. As you can see from the diagram on the right here, we have a small data set with 20 cases, shown as 20 colored dots in the diagram. The cases belong to two classes, shown as red and blue dots. The horizontal and the vertical lines represent the splits we made to partition the cases. As you can see, each split is made to further partition the cases in the partitions created in the previous step. That is why it is called recursive partitioning. If you look closely at each partition only contains cases that belong to the same class. For example, all cases in this partition belong to the red class, and all cases in this partition belong to the blue class. When all cases in the partition belong to the same class, we call this partition a pure partition or subset. So that is how we define pure subset in classification. Achieving purity is easier if you only have a few cases and a clear pattern, as you see in our dataset of 20 cases. But it becomes increasingly difficult when you have a large number of cases and ill-formed data patterns. Therefore, in some cases, achieving purity is not possible or very difficult. The concept of recursive partitioning can be extended to more than 2 dimensions. No matter how many dimensions we have in the dataset, the split search algorithm will divide the entire X space up, either horizontally or vertically, to create rectangles so that each subset is as homogeneous or pure as possible. In the next few slides, we will use a simple example to illustrate how the cases can be partitioned into pure subsets. But to summarize, in classification, pure subsets are subsets that contain cases that belong to the same class. When 100% of the cases belong to the same class in the subset of data, we say that this subset is completely pure. The opposite of that would be half of the cases belonging to one class and the other half belonging to the other class, or 50-50 split in terms of class membership. In this case, we consider the subset to be completely impure. Later on in this lecture, we will discuss how we can quantify the purity or impurity of a subset of data. Also, keep in mind that we have a different definition of pure subsets for prediction problems, which we will discuss in detail when we discuss regression trees. Now let's use a simple example to illustrate the split search algorithm used to build a classification tree. In our example, we have 20 customers who were previously contacted about a home equity line of credit offer. We have their age and income data, as well as whether they responded to the offer or not. The table in this slide shows a portion of the dataset. We can consider this dataset as our training dataset, which is used to grow a classification tree. The diagram in the slide shows the dataset visually, plotting each case according to age and income. We now illustrate how the split search algorithm works to partition the cases into subsets that are increasingly pure. First, we need to identify the possible split points. One look at the diagram shows that there are seemingly unlimited number of possible split points along both age and income dimensions. So which of the split points are relevant to our problem? Well, in decision trees, since the partitions are created based on the training dataset, the only split points that are relevant to our problem are the midpoints between consecutive values of the predictor variables. For example, for the age variable, we can list all values of age in ascending order in this data array: 23, 24, 25, 35, and so on. Please note that some of the cases have the same age value in the dataset, and for ranking purposes, only distinctive age values are listed here. As a result, we have a total of 16 distinctive age values for the dataset. We then identify the midpoints between consecutive values of age. To compute the midpoints, we add the two consecutive values up and divide the sum by 2. For example, the midpoint between 23 and 24 would be 23 plus 24 divided by 2, which is 23.5. By doing this, we create our array of midpoints. There are a total of 15 midpoint values for the 16 distinctive age values. These midpoints are the candidate split points for the age dimension. So, potentially, we can split the data according to the age dimension using the values such as 23.5, 24.5, 30, and so on. Now let's look at the income dimension to identify candidate split points on income dimension. We first sort all distinctive income values in ascending order, resulting in a data array with 20 values. And then we compute the 19 midpoints to create the second array. So potentially, the cases can be partitioned according to the income dimension using values such as 7,500, 12,500, 15,500, and so on. As we illustrated in this example, this is how the split search algorithm identifies candidate split points. The concept can be extended to more dimensions. If there are more than 2 variables, then the same is done to identify candidate split points on other variables. In the example in the previous slide, both the age and income variables are numeric. Therefore, the midpoints of consecutive values are used as candidate split points. And at the same time, we can visualize them on a scatter plot. What if the predicted variables are categorical? Then we will use all the possible ways in which the categories can be split as candidate split points. For example, we have a categorical variable sex with 2 categories, male and female. There is only one way we can split the 2 categories, which is into the male and the female categories. But what about a categorical variable with more than 2 categories? For example, a hypothetical categorical variable with 3 categories, A, B, and C. We can split the categories 3 ways into A and BC, B and AC, and C and AB. What about a hypothetical categorical variable with 4 categories, A, B, C, and D? Then there are 7 potential splits we can make. A and BCD, B and ACD, C and ABD, D and ABC, AB and CD, BC and AD, BD and AC. So as you can see, how the split search algorithm identifies candidate split points is different for numeric and categorical predictor variables. Once we have identified the candidate split points, how do we know which split point should we use to make the first split or the root node of the decision tree? In other words, which of the candidate split points will partition the cases into the purest subsets? As you can see, even with a very small data set with 20 cases and 2 variables, we have a total of 34 candidate split points. If you have a data set with millions of cases and hundreds of variables, the number of candidate split points can run well into millions or more. How do we compare the ability of these candidate split points to create pure subsets in order to identify the best one as our first split or the root node of the classification tree? To answer this question, we need to discuss the measures of purity and impurity. There are multiple ways to measure purity and impurity of a dataset. Here, we are going to introduce 3 most common ones: Gini Index, entropy, and the chi-squared test. Various software products for creating decision trees may use different measures or offer you a choice of which measure to use. Therefore, you should understand how these 3 measures work. Let's start with the Gini Index. The Gini Impurity Index, also called Simpson Diversity Index, is a widely used measure in many disciplines, including statistics and economics. It was created by the Italian statistician Corrado Gini in 1912, and it is widely used as a measure of economic inequity and income distribution. In the case of classification trees, Gini Index can be used as a measure of purity or impurity of a subset of data. It measures how much the split is able to lower diversity amongst the groups. The more the split can lower diversity, the better the split is at creating pure subsets. The formula for computing the Gini index is displayed in this slide. Essentially, to compute the Gini index, you add up the squared proportions for each category, and then subtract the sum from 1. The proportions are computed as the total number of cases that belong to class K divided by the total number of cases. For example, suppose we have two classes, class 1 and class 0. If all cases in the subset belong to class 1 and none belongs to class 0, then the proportion for the class 1 cases is 100%. And the proportion for the class 0 case is 0%. So we compute 1 minus parentheses 100% squared plus 0% squared. And the resulting Gini index is 0. As we discussed before, when all cases belong to the same class, as in this example, this subset is a completely pure subset, and you can't get any purer. This shows that for a completely pure subset, the Gini index value would be 0. Then what about the opposite, or a completely impure subset, where half of the cases belong to one class while the other half belong to the other class? So in that case, the proportion of the two classes will be 50% and 50%. And the Gini index would be 1 minus 50% squared plus 50% squared. And the resulting Gini index is going to be 0.5. So as you can see, for a binary outcome problem, the Gini index can range from 0 to 0.5, with 0 indicating a completely pure subset and 0.5 indicating a completely impure subset. The closer the Gini index is to 0, the purer the subset is, and similarly, the closer the Gini index is to 0.5, the less pure the subset is. Please feel free to test a few different class distributions on your own. For example, a 90% and 10% split, or 70% and 30% split, to see if this is true. Please also keep in mind that we are using binary outcome problems as examples here. If there are more than two categories involved, the minimum Gini index will remain 0, but the maximum Gini index would change. For example, for a 3-category case, the most impure partition would be a 1/3, 1/3, and a 1/3 distribution, and that would lead to a Gini index of 2/3, or 0.67. So in a 3-category case, the Gini index would range from 0 to 0.67. Now that we understand how Gini index works, we can use Gini index to measure the purity of the subsets created by splitting the cases in our previous example of 20 bank customers. One of the candidate split points identified earlier is age equal to 49, which is the midpoint between the consecutive values 48 and 50 for age. Let's compute the Gini index related to this split to see if this split would generate purer subsets. First, let's compute the Gini index for the original dataset before the split so that we have a benchmark Gini index. If you look at all the data points, we have a total of 20 cases. And among the 20 cases, there are 5 customers who responded to the offer, shown as red dots, and 15 customers who did not respond to the offer, shown as blue dots. Since we are more interested in the customers who responded to the offer, respond is the target or success class, or class 1 in our example. And will not respond is class 0. In the original dataset, the proportion of class 1 case is 5 out of 20, and the proportion of class 0 cases is 15 out of 20. As you can see, the Gini index for the dataset with all 20 cases is computed to be 0.375. Please feel free to pause the video and practice how to compute the Gini index. 0.375 is quite close to 0.5, therefore suggests that the current dataset is quite impure. Please keep in mind that Gini index values do not increase or decrease proportionately to the degree of purity. So a Gini index value of 0.25 does not mean that the dataset is half as pure as a completely pure dataset. Therefore, it is best to interpret Gini index values as rankings of purity or impurity. Now let's look at the split at age equal to 49. The split will create 2 partitions in the data as shown in our diagram. On the left side, where all customers are less than 49 years old, there are 16 total cases, 2 of which are class 1 cases, so the proportion of class 1 cases in this partition is 2 out of 16, and the proportion of class 0 cases in this partition is 14 out of 16. With the proportion numbers, we can compute the Gini index for the age less than 49 partition to be 0.2188. This suggests a relatively pure subset. Intuitively, we can also see that in the diagram, the great majority of the cases in this partition belong to class 0 with only 2 exceptions. Now, what about the partition on the right side? There are only 4 cases in that partition, and 3 of them are class 1 cases, so that gives the proportion of class 1 cases of 3 out of 4, and the proportion of the class 0 cases of 1 out of 4. The Gini index is computed to be 0.3750, which is the same as the original 20 cases, suggesting that the purity of this subset neither increased nor decreased from the original dataset. So, is the split at age equal to 49 a good split? In other words, does the split increase the purity of the subsets? Well, in order to compute the Gini index after the split with the Gini index before the split, we need to combine the Gini indexes for the two resulting partitions into one value. This value is the weighted average of the two Gini indexes using the proportion of cases as their weights. For example, the left partition contains 16 cases, which is 16 out of 20 of the entire dataset. Therefore, it is given the weight of 16 over 20, or 0.8. The right partition, on the other hand, has 4 cases, so the weight given to this partition is 4 over 20, or 0.2. The weighted average of the two Gini indexes is the Gini index for the split age equal to 49, and the value is computed to be 0.25. Compared to the Gini index of 0.375 for the original 20 cases, the split age equal to 49 has reduced the Gini index to 0.25, making the subsets purer overall. As you remember, we have identified a total of 34 candidate splits on both the age and income variables for the dataset. Which one is the one that we should use as our first split, or the root node? Well, it is the one that generates the lowest Gini index value, or purest subsets.